Hello students, welcome to another lecture of Environmental Modeling and Simulation. In this lecture, we are going to take one step ahead from the previous lecture and jump into semi-quantitative approach to solving models. Now, this is not purely quantitative, so we are not going to integrate and then simulate and find the exact behavior or the values of the system at any given time. Instead, we are still going to use some very simple principles from a geometric approach. Now, this whole approach is based upon the idea that we can use the concept of potential to understand how the model behaves. So, we know that in our experience, things tend to move from higher potential state to a low potential state, and we are going to use exactly the same principle. So, let's say we make a diagram for a function and we plot the potential function on y-axis and the variable, the one-dimensional variable on x-axis for a system that looks like this: dx by dt is equal to fx. Now we do need to find vx, but I'll tell you how to do that. But let's say this system, this particular system, the curve looks like this. Now, since we know that things tend to move from high potential state to low potential state, if we have an object here or the value of x here, it will tend to move down. And it won't undergo a free fall under gravity. Instead, the movement of x will be determined by fx, by the model, by the system. So please do not expect a free fall, but there will be movement in this direction. On the other hand, if your object is here, if your x value is this, then we expect a movement here. Basically, the x will increase. Same here, if your x is here, the x will move in this direction. So we are expecting an increase in the value of x. So if you look at the system, you can already tell that if something is here, if the x is here, x naught, then it will not move because it is at a place where dv by dx is 0. It is at local minima. It's at a place where the rate at which v is changing with x is 0. So we will not see any movement in this particular plot. There's another point here in this plot where a similar behavior is observed, which is here at the top. So if you're starting with x naught here, at this particular point where dv by dx is also equal to 0, we won't see any movement, any change in the value of x. Now, if you remember the geometrical approach we have been using, such points are frequently referred to as equilibrium points or fixed points. Now, how do we use this potential idea to understand the stability of the fixed point? You can draw the potential if you can figure out v function, but how do we know which of these fixed point is a stable fixed point and which is an unstable? Here it is even more intuitive than it was in the geometric approach. Just by looking at how the potential function is changing with x, you can already tell that this particular position is an unstable position, because if there is any perturbation to the left or the right, the value of x will move away from this fixed point. However, this, which appears to be a local minima, is a stable fixed point, because if there is any perturbation to either left or right, lesser or more, around the fixed point, then the x will return back to the fixed point. So we know this is a stable fixed point and this is an unstable fixed point. Now notice that this approach is actually very easy. It makes decision regarding stability of fixed points quite intuitive. So we are going to understand how to draw this, how to draw the potential functions. Now the problem is that typically the models that we are given look like this: dx by dt is equal to fx. We do not typically get potential functions, especially when we are trying to solve a real world problem or even a theoretical problem. The potential function has to be calculated. How do we approach that? So if you look at this particular diagram, you can see very clearly that the rate at which dv by dx, the rate at which the potential changes with x will determine the rate at which x changes with time, dx by dt. But there will be a minus sign here. And this minus sign is very important because it denotes that the movement happens in the direction so that the potential reduces. The things are trying to move towards the least potential that they can, that they have access to. So the minus sign is important here. Now if we want to find out how v is changing with time, dv by dt, we can split this into dv by dx into dx by dt. And if you look here, dx by dt, you can put the value from this first equation in here. So we end up with dv by dt is equal to dv by dx whole square minus. Now if you notice this function, it's saying clearly that with time, the potential will always reduce less than or equal to 0, because dv by dt is always negative or equal to 0. And you can also very quickly understand that the only instance when dv by dt will not be negative is when dv by dx is 0. And that was the case for these 2 points. dv by dx was 0, so v was not changing with time, and that is our fixed point. Now how do we determine the stability? For that we have to find the v function. So let's do that. Let's find the v function. See, the way we define v function is this, that dv by dx is equal to minus dx by dt. So let's say we have a system and we are going to start with a very simple system. Dx by dt is equal to fx, fx is equal to x. So we have a system where x is changing according to the equation dx by dt is equal to x. Alright, so let's put that value here. So now we have dv by dx is equal to minus x. So we can integrate on both sides, and we get that v is equal to x squared by 2 plus a constant of integration. Now to make our life easy, we can say constant of integration is equal to 0. It's not really important here. And now we have v is equal to x squared by 2. So we are going to plot this vx on y-axis and x on x-axis. So we are going to plot x squared by 2. When x is positive, x squared by 2 will increase like so. When x is negative, it will mirror it and increase like so. Now if you look at this graph, remember y-axis is not the rate at which x is changing with time. The y-axis is the potential. Things move towards lower potential. So if you are starting on the right hand side somewhere here, let's say x naught 1, the thing, your value of x here will move towards left hand side towards the global minima. If you are starting here, x naught 2, again the movement will happen towards minimizing potential. So we know that this particular fixed point is a stable fixed point. Again, we are using a geometric approach, but we are using the principle of potential. Let's try to solve another problem using exactly the same approach. The second problem that we are going to solve is this, dx by dt. So we have a system, a one-dimensional system where x is changing, and the rate at which x is changing is given by x minus x cube. In geometrical approach, I would ask you to draw x minus x cube, find the fixed points, find the value of dx by dt between the fixed points, around the fixed points, and determine the stability. However, using the potential approach, all you need to do is find a function that agrees with this. So if the function that you have, the system you have is very easy to integrate, this approach might be quicker than the purely geometrical approach. So now we have to find v, where minus dv by dx is equal to x minus x cube, and integration is a way to go here. So you get dv by dx is equal to x cube minus x, integrate on both sides, plus a constant of integration. Now again, it's in this case very convenient to declare that constant of integration is 0. So now you are left with v is equal to x to the power 4 by 4 minus x squared by 2. You can plot these two graphs and then understand how you can plot this graph, v on y-axis and x on x-axis. So v on y-axis and x on x-axis, and this graph will look like this. Now, if you look at this graph, without even figuring out what the fixed points are, without even figuring out what the value of fx is between the fixed points, you can clearly find the fixed points. The first fixed point is going to be here, the second fixed point is going to be here, and the third fixed point is going to be here. You are looking for local minima and local maxima. So if around the neighborhood of the first fixed point, which is -1, around the neighborhood of the first fixed point, what you will notice is that the potential reduces in this direction, in this direction. So this is a stable fixed point. Around the neighborhood of the second fixed point, the potential reduces away from this fixed point. So this is an unstable fixed point. Around the third fixed point, the potential reduces in the direction towards the fixed point. So this is a stable fixed point. Okay. So this is how we use the potential approach to understand the stability of the fixed points. I'm going to use another example that we have already covered in our previous lectures, but we use geometric approach, and now we are going to apply the approach of potential. So the third example is dx by dt is sin x is equal to sin x. So we used when we used geometric approach, we just plotted this diagram, phase portrait, dx by dt on y axis, sin x on x axis, and it was a very easy way. And then we had to figure out where the flow is and how the movement happens. Now if you want to use potential approach, because in exam I might ask you, or some other place you might need to use the potential approach, so you need to be skilled at it. We want to find a function where this is true, right? We need to find the function v. Very easy. Dv is equal to minus integration of sin x with dx. When you integrate, you will get v is equal to cos x plus a constant of integration, which for convenience sake we can set to 0, because we just need to understand the behavior of the system. We don't really need to know the value of the constant of integration. So now let's plot our potential diagram, Vx on y-axis and x on x-axis. So we know how cos x behaves. Now the local minima and maxima are your fixed points. So right away we know our fixed points. In this particular domain that I have drawn, I have not drawn the whole cos x, just a part of it. We have one fixed point here, another fixed point here, and the third fixed point here. That if we include this, and even the fourth fixed point here. So we can see very clearly that the fixed points are k, pi, where k is an integer. Now we can also see that here we have a local minima. The potential is reducing towards the fixed point. So this is a stable fixed point. Potential is reducing away from the fixed point, so it's an unstable fixed point. Similarly, fixed point is stable and this fixed point is an unstable. So we already know that for k being even, this particular function will have even or 0. So because 0 is also included in this particular function will have fixed points that are unstable. And when k is odd, we'll be dealing with stable fixed points. So this is how to use the potential principle to understand the stability of fixed point. One more example before we move on. The fourth example is dx by dt is equal to 2 minus sin x. So it's very similar to what we had previously, but now I've added a constant. Now this is very simple, but it's also very important for you to understand what will happen if you have a constant in your function. So to use this approach, once again, we need to find out a potential function so that dx by dt is equal to minus dv by dx. And this is again a very simple case of integration. dv is equal to minus 2 plus sin x integrated with dx, and we'll end up with v is equal to minus 2x minus cos x. Okay, so now what we need to do is plot v versus x. So on y-axis we have vx, and on x-axis we have x, and we are going to draw this diagram. So here I have drawn minus cos x, and now we are drawing minus 2x. So minus 2x will look like this. Now where these two curves intersect separately and understand how the system behaves by subtracting the curves, then I need to make sure that we have subtraction going on in between. So I have already drawn minus cos x, so I can rewrite this system as minus cos x minus plus 2x. I'm going to draw plus 2x. Okay, where they intersect, this is the place where v will be 0, or yes. Now notice here, in this particular case, our net diagram will end up looking something like this. As long as the line is above the curve, which is cos x, we will have a negative value. When the line is below the curve, no matter how the plot behaves, when the line 2x is below the curve, we will have a positive value because line is smaller than the curve. So basically our curve is going to be something like this. There is no local minima. So here we can tell very clearly that in case of 2 minus sin x, there are no fixed points. So we do not need to find stability of any of the fixed points. So this is the potential approach, and now I want to dive into some of the prerequisites that are required for both the qualitative and the quantitative approach, which is that our model should have a unique solution in the time interval in a particular given domain. So this is where we will talk about existence and uniqueness theorem. If our system does not have a unique solution that exists in a given time interval and domain, the qualitative approach fails, and also the quantitative approach. So existence and uniqueness theorem, very simply, because this is not a mathematics course, it's a course for environmental engineers, environmental scientists, and practitioners in this field. Very simply, if your function is smooth enough, if its derivative is smooth enough in a given domain, in a given range of variables, let's say x goes from minus r to plus r, it's an open interval, then you will have a solution for a given time interval, not forever, but for a given time interval. So to use slightly more formal words, existence and uniqueness theorem says that if you have a continuous and continuously differentiable function in a given range, an open range R. So remember, an open range is when we are dealing with, let's say, minus 2 to 2. So we are dealing with all numbers between minus 2 to 2, but not the boundaries minus 2 and 2. A closed range would be like this. So we are dealing with an open range. So as long as within the open range your system, your model is continuous and differentiable, then there will exist unique solutions. Then unique solutions exist for your system, for the model, for given time interval minus tau to plus tau. Not forever, remember that. This is existence and uniqueness theorem. Now we are stepping into slightly more quantitative approach, and to understand quantitative approach, I want to start with what is known as linearizing a system around a fixed point. The biggest problem with analytical approach or quantitative approach that we faced prior to getting very powerful mathematical software like MATLAB, Octave, R was that the calculations were very difficult. And frequently what worked around the fixed point was to linearize the nonlinear system. Now, if you remember in the introductory classes, we spent plenty of time discussing why nonlinear problems are so hard, what defines nonlinear problems, and how they're different from linear problems. So the approach that people would use in quantitative approach was first linearizing your system because they were much easier to solve. So let's say we have a system where dx by dt is equal to fx. And let's say this is one of the fixed points, which means fx asterisk or star is equal to 0. That is when dx by dt becomes 0. So in this particular case, we are going to linearize the function fx around the fixed point x star. Now to determine stability using analytical approach, let me write it down here. Using analytical approach, to find stability of the fixed point. So we have the fixed point, we know the fixed point, we are going to find the stability. So we are going to linearize around this. Now one of the ways that I taught you how to figure out the stability of a fixed point was to introduce a perturbation. So you keep your fixed point, you keep your variable at the fixed point and then introduce a gentle perturbation. So let's say our variable x was equal to x asterisk x star, and now we are introducing a perturbation. So the perturbation is, let's say, represented by this symbol, and this is equal to x minus x star. So this is the new x where I have moved the variable x star or x asterisk is the fixed point where fx is equal to 0. And this perturbation will change with time. So it's a function of time, right? Because it's a dynamic system. So the perturbation will change with time. We want to figure out how the perturbation is changing. Is it going towards the x star or is moving away from the x star? So what we want to figure out is this. Let's do it. So this bracket can be opened up. We end up with dx by dt minus dx star by dt. This is a fixed point, it's a particular point, and then this will be 0. Why will it be 0? Because what we have ended up with is basically fx minus fx asterisk or star. And we know this is a fixed point, so this is equal to 0. So now what we have is the rate at which the perturbation is changing is given by this. We can apply Taylor's theorem here to linearize. So basically we have x. If you go back to this particular system, this particular equation, you can see that x is equal to the perturbation plus fixed point. So we get perturbation plus fixed point. Now you can use Taylor's theorem to expand this, and it will look like so. So we can expand this using the Taylor's theorem, and what we'll end up with is plus higher order terms. So this here represents higher order terms, and we are talking about the order of perturbation, and this will increase quadratically, so they will dramatically go up. Now if your perturbation is small enough, these terms would be very close to 0 as long as this is not 0. As long as f dash x at the fixed point is not 0, as long as the differentiated, if you differentiate dx by dt further, at the fixed point it is not 0, then you can ignore these higher order terms. So let's take a situation where the rate at which perturbation is changing this is negligible compared to this because f dash x is not 0. So we can approximate that the rate at which perturbation is changing is given by perturbation and f dash x approximately. So what we are seeing here is that if the differentiation of your system f dash x around the fixed point, so x star, is less than 0, then the rate at which perturbation is changing will also become negative, which means we are dealing with a stable fixed point. However, if this f dash x star so basically when you derive your function again, when you find these double derivative of x with time, if it is greater than 0 at a given fixed point, then this particular fixed point is an unstable fixed point because the rate at which perturbation is changing is positive. So if you moved your x to the left, it will keep going to the left. If you moved it to right, it will keep going to the right. You're dealing with an unstable fixed point. This approach, where we linearize the system, as I mentioned earlier, is known as linearizing around fixed point. And in the next lecture, we are going to use this approach to understand which of the functions are stable or unstable. To begin with, I'll give a very simple example, and we will use that example to find out whether our fixed point is stable or unstable. So let's say we have a function dx by dt is equal to x square. Very simple function, and we are going to use analytical approach. So analytical approach says first find the fixed points. So for the fixed point, we have to find out when is dx by dt equal to 0. dx by dt is equal to 0 when x is equal to 0 in this particular system. The next step, it says, actually hold on. This is a very different, this is not a problem we can solve very easily using this approach. So let me modify the example, and I will come back to this example, so do not worry. So let's say we are going to use our example is dx by dt is equal to x square minus 4. So we want to find out when is this system equal to 0, and this system is equal to 0 when x is equal to plus minus 2. Yeah. So now what we are going to do is we are going to find, this is fx, we are going to find derivative of x. So we have 2x. Now when x is equal to plus 2, f dash x is equal to plus 4. When x is equal to minus 2, f dash x is equal to minus 4. Greater than 0, less than 0. You know this is an unstable fixed point, and this is a stable fixed point. So students, now you know 3 different methods of finding out the stability of a fixed point. The first method I covered because it is the most different from what is typically taught was the purely geometric approach, where we plotted dx by dt versus x for one-dimensional system. The second was using the concept of potential Vx, knowing that things move from higher potential towards lower potential. The third is the analytical approach, where we linearize around the fixed point. Now, of course, I told you that dx by dt is equal to x square is tricky, so let's look into that. Dx by dt is equal to x square. Let's look at this function, right? Dx by dt is equal to x square when is equal to 0. So the fixed point is when x is equal to 0. So applying the analytical approach, we know that fx is equal to x square, which means f dash x is equal to 2x. Now what happens to f dash x when x is equal to 0? F dash x is also equal to 0. Now, if you remember what I told you when we were learning about the analytical approach, that the rate at which your perturbation changes is given by perturbation f dash x at the fixed point plus higher order terms which increase quadratically with perturbation. Now, since f dash x is equal to 0, this term has become 0, which means this term, the higher order term, is no longer negligible. We can't neglect it. So now we are left with is dn, rate at which the perturbation is changing this very nonlinear system. So we have to now use nonlinear approaches. The linearization around fixed point has collapsed. However, we do have options because we still know the geometric approach and the potential approach. So let's very quickly solve this question using geometric approach. So for geometric approach, we are going to plot dx by dt versus x. And you know the system looks like this. On right hand side, dx by dt is positive, flow is towards plus infinity. On left hand side of the fixed point 0, the flow is towards minus infinity. Oh sorry, dx by dt is positive. So the flow is, x is increasing, so the flow is again towards plus infinity. So no matter where we start, as long as we are not at the fixed point, this system will have a situation where x continues to increase. So you notice here, this is a very, very weird scenario. On left hand side of the fixed point, it's a very interesting scenario. On left hand side of the fixed point, this fixed point is an attractor. So it is stable. However, on the right hand side of this fixed point, this is a repeller. I have mentioned this kind of system in passing. This is half stable and half unstable. In the next lectures, what I'm going to do especially is look into how we can use the tools that we have available with us. For example, Octave, which is an open source software, or a paid software like MATLAB, or another open source software, R, which is very versatile, used mostly for statistics, but also can be used for modeling, to figure out how the system is behaving, what are the fixed points, and are they stable or unstable, and how the slope lines look like. This is all for today. Thank you. See you in the next lecture.